In this video, I want to talk about two specific methods for mitigating database stress. But first, I want to define this term of stress. What do I actually mean when I say a database undergoes stress? I would say for the sake of this video, we can think of stress in two different ways. The first can mean a lot of different users or clients trying to connect to our database at the same time. So in the last couple of videos, we've talked about concurrency and how that means that a database is trying to process a lot of different operations at the same time. So this sense of stress can mean that a lot of different users are trying to connect to our database to execute those sort of concurrent operations. The second way in which stress can be talked about is the actual amount of data in the database. So you could imagine for some really large institutions or organizations that have really large databases, they have a lot of data that needs to get stored. So how do we handle distributing that data and making sure that all of the load isn't in only one place on one system on the hardware of only one device? So let's talk about the first instance of stress with a lot of concurrent users trying to connect to our database. We're going to talk about something called connection pooling. So let's walk through a little scenario. Let's say that we have a client that's trying to connect to our little database over here on the right. If you haven't seen this before, this is just simply a sort of easy sort of understanding of what we think databases can look like. For a lot of diagrams and stuff, you'll see a structure that kind of looks like these little cylinders. And this is what's going to represent our database here. And then I have this little cartoon computer over here, which can represent a client. And, for the sake of, having multiple concurrent users, we can have a couple of these guys, and then we'll have just three. And essentially, let's say that each of these clients is trying to connect to our database. So without connection pooling, if we're sort of thinking about this problem in a very simple way, we have each and every one of these computers connecting directly to our database and trying to execute all of their operations. If you need to think about this in terms of an example, we can reference the example from our earlier videos of having like a bank account database where the different tables in the database can store information about the clients for that bank, having their account information, their account balances, all sorts of things like that. And these clients could literally just be people that are trying to access their accounts, whether that be for withdrawals or updating their information in any way, checking it in some way. But you can see how this can get messy. You could imagine for big institutions, a really big bank or something like that, in this case, there could be hundreds of these little cartoon computers that are trying to connect to this database. And in that sense, there's a lot of concurrent operations that need to go on for this database, but also these individual connections, there's so many of them. And this isn't necessarily a really simple thing to facilitate this little connection. So in fact, each of these individual connections requires some resources themselves. They not only require memory, but they also have a lot of work on the part of authentication and network setup. There's something called like the TCP or like network handshake. And this is a really expensive operation for the database over here. So what this means is that each individual client, like let's term this computer C1, for each of these individual clients that connects to the database, there is some work on the database's end to actually uphold this connection. Specifically, there's a lot of operating system resources that are used to maintain, close, and sort of keep these connections running in the first place. And they have to sort of connect to a lot of these backend services, and that's a pretty expensive operation. The actual number for how much memory one of these connections takes, I think varies, but I've been seeing reports of up to like even 1.3 megabytes for one of these connections, and even more, honestly. And so you can imagine with hundreds and hundreds of these connections, or thousands, or even millions of these connections, the resources will add up extremely quick. So it can be really dangerous to just have unlimited connections straight to the database. And also, it's kind of like you're sort of redoing this exact same process over and over again. So as soon as client one connects, you have to do this sort of authentication, set up the memory management, do the network handshake, all of that sort of stuff. And then for client two, you do the exact same thing. And then client three, you do the exact same thing. So What connection pooling says is instead of doing any of this stuff, what we should just do is have a sort of steady rate of connections that exist in our database. So we can have sort of some predetermined connections that have already been created, and we'll say this is the pool of connections, and these are a set amount of connections that connect to our database. And for this, we've already done some of the work in terms of memory management and the handshake and things like that. But instead of actually having every single computer connect individually to our database, what we do instead is we have the computer actually request a connection from our pool. And this means that instead of having to allocate some new resources for a new connection, what we can do is simply say, hey, you're looking to connect to our database, let's just give you this connection right here. And then client 2 over here is trying to connect to our database as well. We can assign them a connection as well. So you can kind of see the difference is that we have these sort of set allocated resources to connect to our database, and instead of creating a new connection every single time, we can reuse from this pool of connections that already exists. So that means there's a fixed amount of resources that's kind of allocated in this part, and we don't really have to worry about however many clients try to connect to our database. And so the way this kind of allocation works is kind of on a use, borrow and return sort of cycle. So if we're kind of breaking down the way that this system works, we can map it out in terms of a couple of steps. So let's write them out. The first step sort of looks like this. We can have the actual initialization, and we can think of the initialization as just sort of the creation of all of these connections in the pool. So this is initializing some sort of connection to our database and storing all of those together. And then the second can be the connection request. So that is this part of the equation right here, where we're basically allowing our clients to make connections to our database. And this is actually a really important part because this is what allows this sort of connection between our already created resources and the new ones that are the clients that are trying to connect to our database. The third step can mean the actual usage. So this is the really important part of what's actually going on when we do this connection pooling. So C1 has some sort of work that they want to do in the context of our banking example. Maybe that means they want to add $200 to a bank account or subtract $100 from their bank account, any sort of number of operations essentially. Whatever they're doing, the work is actually done through their connection that's in the connection pool. Then after is the return. So after this client is done using their connection that's in the pool, they simply return it to the pool and it's ready to use for a different client. Then the final thing, like I was saying, is the reuse. So once everything is done, we can reuse that exact same connection. And this is just in essence how connection pooling works. There's some specifics in terms of how we actually authenticate some of these requests that are coming into the pool, but the essence of the idea for connection pooling is simply that. Reusing the same connection to the database so that we don't have to allocate some really expensive resources and reinvent the wheel every single time that we're creating a connection. But now let's think about that second scenario of stress where there's simply a lot of data to store in our database. And we can imagine there's also simply the problem at the same time of a lot of clients trying to connect to our database, because this next part that I'm talking about kind of addresses both of them. But what we're going to talk about is sharding. So to help think about this problem, what I want to do is bring up a picture of a broken vase. And so you can imagine at one point this vase was probably whole. And in the picture, it's kind of been broken into these different shards. But each one of these shards still has some information that is related to the larger vase. For example, that could be in that this little flower that's here or here was still once part of this vase. And if you actually put everything back together, you would have the whole and complete vase. this is kind of a simple analogy for understanding how sharding kind of works. But essentially what sharding does, and I'll write out this term for clarity, is it breaks this database into different shards that are accessible in different places. And it makes it a lot easier to have distributed storage and decreased latency for the queries that our users and clients actually want. So what this looks like in terms of this database model is this. So you can imagine we have this larger database here. And just like our earlier model, maybe this could pertain to a bank. And now we're splitting it up into 3 separate shards. This first shard maybe has some portion of the database, like some portion here. The second shard has another portion, and this third shard has the last portion. And so essentially, each shard will contain unique rows, and this is sort of stored across multiple computers, and those computers are all called these sort of nodes, is an easy way to think of it. So shard 1, 2, and 3 are all separate nodes, and each of them operate independently. So you can notice what I said earlier was that these are all run on separate computers. So that comes with its own inherent advantage, which is that each of these being run on different computers increases the storage capacity. So you could imagine if everything is run on one computer, if we have just this database on one computer, there's some actual storage limit that's there. But you can imagine if you have multiple shards and they're all run on those same computers, but in different places, then you have already way more storage. So in one sense, this has already solved the problem of enough storage and having a lot of data to store. But shards are actually super unique in the sense that they solve another problem too, which is that we have a lot of requests kind of coming into the database, and we don't want to have users who are requesting things from our database have to wait a long time to get that information. So right, let's say we have our little client here again to connect to our database. So this client can be just someone again who wants to query our database, get some information, but let's say that they want to access information about their account. Since we said that the database is now sharded into these 3 little pieces, the client actually doesn't have to connect to the whole database. They instead only have to connect to the shard that has the specific piece of information that they want. And the reason this is beneficial is you can imagine as we scale up and we have hundreds of thousands of users, even more even, each of those clients doesn't have to route to the same device even. And so when you're thinking about this in the context of resource allocation, the load of the resource allocation is distributed across each of these shards. So there is way less of a demand of resources on just this general whole database. And that, as you scale up, becomes extremely, extremely important. But how do you decide what information goes into what shards? Now, I'm going to talk about 3 different methods for how we can actually allocate information into these shards, which help us denote sort of where to put things, what box to drop it in, and how we should route clients to that. So the first method that I want to talk about for splitting things into shards is range-based. So these are in some ways these different methods are kind of in some ways referred to as shard keys, because they kind of tell you, hey, this is the shard that we should be dropping this information in. But range-based is pretty simple to understand. It's kind of just sort of splitting up the information based on a range of values. So you can imagine for our bank database example, if we split up the information based on the last names of the customers, we could split up the information based on the range of the alphabet. So let's say this first shard, actually I'll clear up some of this mess here so that it's easier to see. But we'll say that this first shard right here contains, let's say, last names A to I. Then we can have the second shard be last names J to P, and then the last names Q to Z in the third shard. Now what this does is it takes all of these rows with the clients and information in the original database, and it puts it into these 3 different shards right here. And now every client, if they have a last name with a letter between A and I, only has to access shard 1. they won't actually need information that's coming from shard 2 or shard 3. And that's really important because then the load is kind of distributed. But you can notice this might actually cause some problems to arise. For example, let's say like a bank has way more clients with last names from J to P. Then the load is kind of unevenly distributed across shard 2, and then shard 3 and shard 1 aren't actually having as much of their compute resources being equally used. What this means is that probably range-based sharding, or at least ranges based on the last name, is probably not a good idea for this database. Now, you can set ranges based on any number of things, like it could be like maybe even account balances, so people with like lower or higher accounts have to access a different shard, but you also can like just use a different method entirely of splitting up the information. The second method I want to talk about is hash-based sharding. So what this does is essentially has some sort of encoding or a hash function that determines which shard you're placed into. And again, I'll clear this up to sort of walk through an example, but you can imagine there's some sort of, hash function, and then into that function you could pass in maybe a row or some value. Let's say this is my information and it has some like account balance sticking with that bank example, and then it has like an account ID. Like you can imagine this is some like tuple in the database. Based on this function, there would be some output. And for simplicity, we'll say that it just outputs like a single shard number. Like it will tell us that it outputs the number 3. And this means that all of that information goes to shard 3. But realistically, in the real world, I feel like this would probably be some sort of range of values, but this is essentially how hash-based sharding works, where it'll output some sort of number which indicates which shard it'll go to, and based on what the hash function is defined as, will kind of affect just sort of where things are placed and the load of the different shards. But the final method I want to talk about is a method that's called directory-based, or sometimes lookup-based sharding. And I'll write that here. Lookup-based or directory. I think either of those are kind of interchangeable, but we have this little diagram here which kind of explains things pretty nicely. So directory-based sharding is kind of like having a lookup table inside your database, which basically tells the client or the router where they should be looking for the information. So you can imagine in this example, in this diagram, you see we have an actual database with some information here with a customer and a location. And this location is how they're actually like sharding their database. So essentially, if there is a client who's from North America, they want to access that information, then we know we need to go to shard 1. If they're from Europe, then they go to shard 2, and so on. So this lookup table is what actually provides the information for where we should be looking for the information. And so this directory-based sharding is kind of just taking an entire category of information and you're splitting your database based on that. And again, with all of these, there can be sort of uneven splits of data. If you have a table or a database with way more people from North America, then obviously the load, the requests, everything, the resource allocation is going to be unheavily distributed on shard 1. So in that case, you would probably want to pick some sort of different split or some different way to shard the database so that the load is more evenly distributed across all shards. But in essence, this is how a lot of these sort of methods work. And there are more methods out there. There's, for example, something called geo-based sharding. But we've covered the sort of big few examples and probably the most common examples that you'll see if you're looking into database sharding and how we can organize a database better. There are other methods as well for how we can mitigate load across a database. Load balancing is something that's really important that I want to talk about as well. But just for the sake of these two examples of stress, I wanted to talk about these two examples of connection pooling and sharding.